Hello, everyone. I'm Alex Utsa. I'm an assistant professor at Leiden University in the Netherlands. And I'm one of the chairs of this HotCloudPerf workshop, the third edition. I'm actually happy that today we're making this happen, as well as the ICP conference, because with all the negativity happening, it's actually good to have a meeting, talk about things we like and enjoy, and we have this sense of community. And I'm also happy that we have at least now 63 participants, which is quite a lot for a workshop in general. So that's also a very positive outcome. So thanks for all the participants. It's very nice to have you here. And as well, I'd like to thank the other co-chairs, so Dimitri, Christina, Nicolas, Alexander Yusuf, the PC members who helped us a lot in organizing, as well as the authors for their great work. And I also like to thank the keynote speakers for agreeing to do this. I know it's a bit more difficult to do a presentation when you're not in the same room with everybody. So thanks a lot, Rob and Tim. This HotCloudPerf workshop is technically sponsored and organized by SpecRG Cloud Group. So you're gonna hear more about that towards the end of the session of today. And the topic of this year is cloud performance variability. And today we're going to have two sessions. The first one for about an hour, we'll have two keynote speeches. And the second session for also about an hour, we'll have three paper presentations and some short presentation about SpecRG Cloud Group. And now, to begin the first session, I'd like to pass the mic to Christina, who is going to chair the keynote session.
Yes, thanks, Alex. Can you hear me? Yes, right. Okay, so I'm Christina. I'm a professor in Spolin University in Guayaquil, Ecuador, and also one of the co-chairs of HotCloudPerf. It is my pleasure to introduce the first keynote, Robert Ricci. He's a research associate professor in the School of Computing at the University of Utah and lead of the Cloud Lab testbed and was the director of Flux research group. He works in computing, including networking, distributed systems, and cloud computing. Robert has worked on EmuLab and its successors, including Cloud Lab, Arts of Genie, and Power since 2000. And one of the things he also works in is in research reproducibility. So please go ahead, Robert.
All right. Thank you very much, Christina. So let's see. I hope that I am sharing at this point. Is that correct?
Yes, it looks great.
Okay, great. Yeah, so as Christina said, I'm at the University of Utah. I am going to talk today about gathering reliable performance measurements in the cloud. So as I'm sure that everybody at this workshop is aware, there are a lot of sources of variability when you try to gather performance measurements in the cloud. In fact, that's, as Alex said, that's kind of the theme of our workshop this year, right? So there are some that are pretty well known that we're all familiar with, such as other tenants on your own host. We often call these noisy neighbors. You may interfere with other tenants who are not on the same host, right? Who are causing congestion in the network or on the storage system or on a shared storage system. There are also, though, less obvious sources of variability, such as the policies of the cloud provider and differences in the cloud provider hardware, and even different versions of the hypervisor that the cloud provider may be running on different machines in their data center. Even things like the environmental conditions inside the data center, heat in various parts of it, things that are really not at all visible to you. And then, of course, there's your code or the system that you're trying to actually measure, which itself probably has some variability. And what you want to do is sort of understand when you are taking a measurement, kind of where the variability that comes from your code ends and where the variability of the facility itself starts. So with this, I maybe should sort of retitle or come up with another question or rephrase my talk as a question, right? Which is, can I get repeatable and reliable performance measurements in the cloud at all? So what I'm going to do for the rest of this talk is go over some results that I and some of my collaborators, many of whom are in this workshop, have gathered over the last couple of years, and talk both about some of the challenges in getting reliable performance numbers on the cloud and some mitigations that we can apply to get reasonable numbers despite the fact that these challenges exist. And I'll provide some more bibliographic details on those papers at the end. So let me start with a relatively easy one, which is stochastic network noise. So what we're looking at here is some bandwidth numbers that were gathered on Google Cloud over the period of a few weeks. You'll notice that the time is in the hundreds of thousands of seconds. And don't worry too much at the moment about the different colors and what full speed and so forth means. I'll talk about that more in a later slide. But what you can see here is that we have something that looks like a pretty stable baseline performance. There are a couple of noticeable events where the bandwidth that's available to us drops. But overall, this is a system that is fairly well modeled, with there being a true median performance and then some stochastic random noise. And the good news is that this is relatively easy to mitigate, right? We know how to do this. Essentially, we just need to do a whole lot of runs, right, of our experiment and use statistical tools to actually model how confident we can be in those results, right? So, if it's been a while since you've seen something showing confidence intervals, I've just got an example up here. So what we see here is we're measuring a median, which is the heavy blue line in the middle, and we're looking at the 95% confidence intervals, which is the shaded purplish part on both sides of that. And this is a fairly well-behaved chart where we do more runs of the experiment, and the median kind of quiets down. You can see it's initially noisy over here, and it kind of quiets down as we do more runs. And you can see that the confidence interval is pretty wide to begin with, and later on, again, as we do more runs, it narrows down, which is a good thing because it's essentially giving us the region that we can be 95% confident that the true median lies in, right? So being narrow is a good thing because it tells us that we probably are, the median that we're reporting is probably quite close to the true median. So that was a relatively easy case. Let's look at a more complicated one. So these are some latency numbers that we gathered on AWS. And this is the good case. This is the normal case that we see in AWS. So if you look at the left graph, the latency, you can see again we have kind of a clear baseline performance, with a fair amount of random noise. Again, there's a couple clear events here, but mostly they're rather small, and we can model the system as random noise. And our bandwidth over here is quite steady. So that's the good case. If we look at some other graphs that were also gathered from AWS, we can see that everything has kind of gone crazy, right? So here, notice that the latency has actually increased by an order of magnitude. It's no longer it no longer looks like random noise. There's some clear structure to it, and our bandwidth has dropped by an order of magnitude. So what's going on here? Well, in this case, we are having an unfortunate interaction with policies of the provider. So in this case, AWS has an undocumented bandwidth cap that it applies on virtual network interfaces. And what we're seeing here is that at about this time, we hit that cap, which is maintained through a token bucket. And so essentially our traffic starts getting shaped. And so our bandwidth drops to the new traffic shaping level, and this behavior is actually, you're seeing kind of the classic TCP sawtooth as it's increasing its window and seeing increasing latency and finding the correct bandwidth. So in addition to being kind of annoying from a performance point of view, the other problem is that this actually breaks the statistical models that we use to try to, report our results. So here I'm looking at another graph showing confidence intervals. Again, we have the median as the dark line in the middle, and then we have the shaded area around it that's showing our confidence interval. And what we're doing in this experiment is, I mentioned that this behavior is enforced by a token bucket. So each of these things here that gives a budget number, what it's doing is it's giving us the number. We're emulating the behavior of running repeated back-to-back experiments where which is what you would typically do in a environment where you're trying to get more better data by doing more runs, and we're decreasing the budget every 10 experiments, because again, this is a model of what is actually happening in AWS. And so what you can see here is that this is actually not a well-behaved confidence interval plot, right? So up for the first part, we have pretty good confidence intervals, and as we expect, as we run more experiments, they're at least not getting worse. But then when we hit the point where the token bucket is starting to actually affect our experiments, as we're doing more runs, our confidence interval actually gets wider, right? Which is not supposed to happen. And what's happening here is that the statistical tools assume that you have a stationary distribution. In other words, the parameters of the distribution do not change over time, and that each run is IID, so independent, identically distributed. And what we have here is kind of you could think of it as either self-interference, where our earlier experiments are interfering with our later ones, or as interference with the provider policy, and so they're not actually independent. This particular graph came from running a TPCH benchmark on AWS. Unless you think that this is kind of a rare occurrence, we ran a much larger set of TPCH benchmarks, and actually about 80% of them exhibited behavior like this. This is a particularly extreme one, but this kind of behavior is actually quite common among these different benchmarks. So, how do we mitigate this? Obviously, this is trickier than just do more runs and apply statistics. So one thing we can do here is we can rest the instances. So in this particular case, the token bucket has filled up, right? Has emptied, I should say, and we can rest them and let them sit for a while and let it, in order to let it recharge. This is tricky because this is undocumented behavior of AWS, and so we had to kind of reverse engineer the parameters for the set of instances we were using, and they don't actually directly expose to you what the current state is until it's empty, and so it's imprecise, right? And you may have to let it rest for 10 minutes, half an hour, or so forth between experiments. Another option is to use clean instances, where you bring up a new, fresh set of VMs for every experiment you're going to run. This can actually help you run your experiments faster, because you can run a bunch of experiments in parallel instead of in serial. But of course, it requires other kinds of automation, and it potentially exposes you to more types of variability, because now you're running on a much wider variety of different hosts. Another thing that you can do to help, it doesn't make this effect go away, but it can help reduce the bias in it, is randomizing experiment order. So like, let's say I was running an experiment where I was trying to produce a graph of scaling as a function of the problem size that I was inputting to a particular algorithm or distributed system. So if I was to run in an environment where in an experimental design where I try all the small experiments and I gradually ramp up the problem size as I go, as you would see, the small experiments would encounter this behavior, the large experiments would encounter this behavior. So I would be, kind of systematically biasing my experiment environment against the large experiments. And so, at least running those in a random order instead of a sequential order is going to help me remove that systematic bias, even if it doesn't make the effect actually go Okay, so let's look at another tricky environment to deal with. So this is, again, I'm showing you the bandwidth data that I showed you from Google Cloud earlier. So this time, let me explain a little bit more what these different experiments are. So we have the full speed, which is the green, which is largely clustered up here at the top of our graph. And what this is essentially we're opening up a TCP socket, sending data as fast as we can through it for a long period of time, essentially maxing out the bandwidth. Of course, many applications, like big data applications, are not going to spend all of their time sending and receiving data. They're going to, receive data, compute, send results, compute, receive data, compute, etc. So this 1030, the orange color, we're transmitting for 10 seconds, then resting for 30 seconds is a sort of a crude model of a big data application. And 530 is a similar thing, but we're transmitting for 5 seconds and then resting for 30 seconds. And again, remember, this is over a period of weeks, right? We're seeing this is hundreds of thousands of seconds. So what we see here is that the behavior that our foreground application is exhibiting actually affects the amount of variability that it sees. So the full speed and 1030 flows are, seeing fairly tight variability behaviors, whereas this one where we only transmit for 5 seconds and then rest for 30, we're actually seeing very large, or proportionally larger amount of variability. We think, by the way, that what is probably going on in this case is that Google actually has a nice paper about how their network works in their cloud data centers. And one of the things that it talks about is they do some caching, essentially, of routes, so that if you've been transmitting a lot, you get basically a more direct route to your destination instead of having to go through some of their central routers. And so probably what's happening is our 530 setup is running afoul of this, sometimes getting evicted from the cache and having essentially a slower start before it gets added back into the cache. So this is an example, we believe, though we don't have sort of more concrete evidence of it, of a weird interaction with the implementation that the provider has of their virtual machines. So mitigations for this are a bit trickier in the sense that part of it is we just have to understand that sometimes we're measuring artifacts of the cloud provider itself versus fundamental properties of the system that we're trying to measure, right? So in this case, if I'm trying to compare two systems and one of them behaves like the 1030 experiment and the other one behaves like the 530 experiment, the level of the variability that they're going to see is in part just an artifact of the cloud provider we're running on. So we could consider, hey, let's try testing this out on different clouds, right, to minimize seeing those artifacts from one cloud provider. This is a good idea, but there are other gotchas when you do this, right? So here we're running those same 3 experiments. The graph that I'm showing you right now is from Google Cloud. What we're seeing, what we're looking at is, again, this is experiment, TCP experiments run over a long period of time. And then on the y-axis, we're seeing the cumulative amount of traffic that we've been able to transfer. So, kind of as expected, this full speed one that is not resting is able to transmit, more traffic than the other 2. And they're all nicely, the cumulative traffic is all nicely linear as you would expect from this kind of system. Unfortunately, if we go and try to run that on AWS, what we see is actually, notice that this, my y-axis is now an order of magnitude lower. And the full speed experiment is not actually transmitting that much more data than the ones that are actually having these big pauses in their transmissions. And again, this is a interaction with that token bucket in AWS that's limiting our speed after we transmit a certain amount of data. So, we can do this, we can run on different clouds, but we have this problem where essentially we can't really assume that results that we gathered on one cloud can generalize to another cloud, right? If system A is faster than system B on AWS, it might be faster on Google Cloud, but it also might not be faster. And if we want to be able to say sort of more fundamental something more fundamental, something deeper and broader than just, system A is faster than system B on AWS. We may need to actually run this on multiple clouds in order to get support for the hypothesis that this is something fundamental and not an artifact of a particular cloud that we're running on. So to come back to my initial question, can I get reliable performance measurements in the cloud? The answer is yes, but right. There's a lot of methodological things that we need to do. Probably doing a lot more runs than you're doing already. Checking for the statistical properties that your statistical tools are assuming, things like normality, stationarity, whether or not they're independent, identically distributed. It's also important to report measurements of variability and/or confidence, so that the reader understands whether these results are very consistent or whether there is a fair amount of variability in them. I talked about running on fresh instances or resting between experiments, and then another thing, of course, that we're all, I think, aware of that I didn't go through it in the talk, is that we all know that there are like diurnal variations in traffic patterns and usage patterns of various web services. So you also probably need to try to capture that in your experiments. And also the unfortunate fact is that results you get on one cloud probably don't generalize across clouds. They might not generalize across time, right? Cloud providers can and do change some of their implementation details and their policies. We ran into this in the middle of some of those experiments that I was talking about, where they changed the speeds of the virtual NICs that we were getting partway through our experiments. And unfortunately, results you get may not generalize across instance types or availability zones. We have some evidence that different instance types have, for example, different implementations of the host VM networking stack, right? And different availability zones may have slightly, maybe some that are newer than others may have different network topologies. So I have like about 2 minutes left, and so I'm going to try to ask another question really quick, which is, do experimenters even try to get reliable performance measurements in the cloud? So for one of our papers, we did a survey of major systems conferences, including things like SOSP, NSDI, supercomputing, and looked at papers in them that explicitly said that they had run their experiments in the cloud. And kind of one of the big takeaways here is that more than 60% of the papers did not really tell us enough about the experiments they ran for us to be able to know how rigorous their experiments were. Many of them didn't tell us whether they were reporting the average or median, for example, which is a pretty basic thing that you need to know when you're looking at performance numbers. Many of them did not report any measure of variability. They didn't report quartiles or variance or even confidence intervals. And when they did tell us how many runs they did, which many of them did not, as you can see, most of them are looking at things that are like 10 repetitions or fewer. And most of the data that we have suggests that you for some experiments you may need up to like hundreds of repetitions to get statistically good results in the cloud. So the answer to that question is no. Most people, or at least most people, are not taking the reliability of their numbers in the cloud very seriously, unfortunately. And the papers that we looked at in the previous survey were pretty influential ones that collectively have thousands of citations. So they're not unknown fringe papers. So I want to end with a call to action and say, like, we can do better, right, in terms of getting these reliable performance numbers. We can apply down statistics. We can report in more detail the procedures that we actually use. As much as possible, we should report baselines. Like if you're going to, run some micro benchmarks, right? Run network benchmarks or test the flops or something on your VM, so that when other people go to try to replicate your experiments, they can figure out whether they're getting similar numbers to what you got. We really need a lot more studies of reproducibility in the cloud. As you may have noticed, most of the numbers that I presented earlier were about networking, which is, one part of cloud reproducibility, but of course there's lots of others, storage and compute performance and stuff. And there are some things like this, but they're not extremely systematic, and a lot of them are actually done in security context where it's about leaking information, and we should do this for reproducibility as well. And then finally, a lot of the experiments we run could be run in more controlled environments, right? So some of them need to run in the cloud because of their scale, or because we're very specifically interested in how they perform in the cloud. But in some cases we could be running in environments that are more controlled, and save ourselves a lot of headaches in terms of dealing with some of these challenges. And in full disclosure, I do run one such environment, Cloud Lab. So I am a little biased in saying this, but we can save ourselves a lot of headache by not running in the cloud when we don't have to, not running in shared environments when we don't have to. So with that, I'm ready for questions, and I just wanted to say that the figures that I presented here and those conclusions come from essentially two papers, one by Alex Utsa, Dimitri Dupliakin, who's also on, and others who are on the workshop as well, such as Alex Yusuf, that we published a few months ago at NSDI 2020, and another one from OSDI 2018. That Dimitri and I believe Carlos Maltzahn was one of the authors on that paper as well. So we have more details about a lot of the stuff in those two papers. So thank you, and I'm happy to take questions. I've not been watching any of the text chat, so if there's any text questions, I haven't noticed them.
Yes, thanks, Robert. Actually, there's lots of very great questions.
Good, excellent. Let me see. Let me stop. Oh yeah, if you want to read them, that'd be great. Or I can stop sharing my video so that I can read them.
I mean, sure. Either way. I mean, I can read them. I can read a couple.
Why don't you go ahead and read some of them? Thank you.
Yes. So people are wondering, what about the new burstable instances in AWS and EC2? Also, they're asking how we could do experiments. As actually people that do experiments do more repetitions and provide other results to make them more credible. And even for very large scale experiments, perhaps having them register beforehand. Like in other sciences, they do this. They have to say what you're expecting out of your experiment.
Yeah. So let me take, I'm sorry, go ahead.
No. I was going to say,
okay.
Go ahead, please.
Yeah, so I'll take the first one, which is that on the burstable instances, I mean, essentially, I don't know. We haven't run stuff on the burstable instances. And an unfortunate fact, I think, is that, different instance types do seem to have, so for example, in AWS, there's some of them that are listed as having enhanced networking stacks and other ones that are not. The ones that I reported on are actually from the I believe they're from the C5 class, which is commonly used in big data experiments, which does have this enhanced networking. But there's a pretty good chance that a bunch of these instances have slightly different implementations of some of the core pieces. And the only real thing we can do as experimenters is to try them, right? And one of the differences between commercial cloud providers and some other facilities like the Cloud Lab that I run is that, of course, the commercial cloud providers, to some extent, have business reasons for not exposing this information and data to you, because they don't want, for example, their competitors being able to figure out what they're doing. They don't want, there are certain things that they probably are concerned might, drive their business down. Of course, many of these decisions are made for many of the they make a lot of decisions for performance reasons that are sort of good for most of their customers, but bad for people who want to run repeatable experimentation. So like the Google Cloud one that I mentioned, which, I mean, that's great. They do have a paper about it. So actually we know probably more about the Google Cloud network implementation than we do about AWS's. It is a design that probably serves most of their customers extremely well and allows them to do it at a reasonable cost and to get reasonable performance, but does get in the way of repeatability. And actually, this is something we've noticed in a lot of our repeatability experimentations, is that often the simpler machines have worse performance but are also more repeatable, right? Things like, the more branch prediction you're doing, the more bigger cache you have, the harder it is to reproduce experiments. So I know I didn't directly answer the question about burstable instances, but essentially we have to try them, right? On the next question about registering, I mean, obviously this is something that is fairly alien to our community. I think it would be very interesting to run kind of some trials there, and try it with some workshops, try it with some conferences, and kind of see how that goes, right? I don't really know what would come of such an experiment, and it might be worth doing. And I think, Christina, I think there was a third one that you mentioned that I've actually forgotten already, unfortunately.
No, I mean, there's lots of more questions,
Okay.
but I just mentioned those two. Let me try just one last one. Kumar, can you maybe unmute yourself and ask your question?
Yeah, so I have a small question, like a couple of questions really. So one is, usually in production, we don't get a clean slate like in test environments. So
Yep.
how reliable will our results be if we run the test with clean slates or clean instances in our environment?
Yep.
That is one.
Yep.
And second, I just to add that the other question as well. In usually what I've observed, and based on the feedback, there is an element of network latency in the cloud environment. So is there something we can do to model our performance tests to mitigate those limitations? Those are the two questions.
Yeah, so those are two excellent questions. To answer the first one, I think it depends a lot on the goal of your performance analysis, right? So in many cases, in an academic setting, which is primarily the community that I am in and interact with, the goal is to try to demonstrate kind of things that are fundamental about certain algorithms or system designs or whatever, because we as academics don't necessarily have access to workloads that are as realistic, as what you would. I mean, obviously, what you see in practice is reality, right? Or may not have, while we may be able to run in a commercial cloud, we may not be able to run in the exact environment that a particular company operates in production, right? So for that kind of work, I think that the value of a more controlled environment or something that where you have taken pains to run lots of experiments to get a quote unquote clean number, or to do these rests. The value is that it helps you expose kind of what is more fundamental as opposed to what is an artifact of the environment that you're running in. But of course, when you're going to run stuff in production, the artifact of the environment you're running in is super important. And so I think it can be useful to have both of those perspectives, because actually having an understanding of how your system behaves in a clean slate can help you understand what behaviors you're seeing in production might be, artifacts of that environment, right? That are something that maybe you can do something about if they're problematic, right? The other question, latency. I mean, one big difference, for example, between EC2 and Google Cloud that I didn't cover in this talk is that actually their latency performance is actually quite different. At least with the instant types we used in the availability zones we used, I don't know how much I can generalize past that. AWS had much lower latency, like almost a factor of 10, I think. In Google Cloud, it was much higher, and that's probably again an artifact of how they've chosen to implement their network stacks. And I think in AWS's case, it's probably in part because of the policy, right? I expect that their policy of limiting of rate limiting your bandwidth after a certain point probably helps contribute to a lower latency, actually, right? And that's one of those, it's one of these things where, you know, essentially, I think kind of the best you can do is measure it and explain to people the conditions under which you ran your experiment, so that if they see something different, they can try to begin to understand, oh, you know, when Rob, you know, got this, he was, you know, seeing, you know, 0.1 millisecond latency, and in the environment I'm running it in, I'm seeing 1 millisecond latency, and maybe this in part accounts for the differences in what I'm seeing.
Thank you so much, Robert, for answering the questions.
Well, thank you very much, and I'm happy to. I'll keep taking questions on Slack and stuff. And as I mentioned, like many of my collaborators are on, and I'm sure that they can answer some of these questions even better than I can. So.